The following is a video on ordered hashing part 5. This form of hashing is based on the idea of using data to denote or to represent an operation. Thus, in this case, we have ordered hashing number 5. So it's based on the simple idea of using data to denote an operation, actually stand for an operation. Thus the value of 0 will be used to stand for the operation of minus, and the value of 1 will be used to denote the operation of plus. Okay. Now our objective is to code a number m equal to 2 power L dash as a value with an s equal to 2 power L, where L dash is again very much larger than L. Now since we are using, the idea is to use a bit value to stand for either a plus or a minus operation. Now we can rewrite m, we know that we can write m as m times half plus 1 by 4 plus and so on up to 1 by 2 power n. Now our objective is to have exactly L plus 1 ratios. That is for S. If these are the L bits of S, we have S here and there are L bits here, 0th bit to L minus 1 bit. Each of these bits represents an operation plus or minus. So in all we will have L plus 1 ratios associated. Each ratio must be less than 1. Their differences starting from the leftmost one must, if you subtract all of them, must come close to 0, and if you add up all of them, they must come close to 1. All of these ratios must be less than 1. So the obvious one, like we just saw, is 1 plus 1 by 2 plus or minus 1 by 4 plus or minus 1 by 8 plus or minus 1 by 16. This will only come up to plus or minus 1 by 2 power L. But L dash is much larger than L, so we would like the last value here to represent the value 1 by 2 power L dash. To that end, we proceed as follows. First, we start off with the ratio half. Then we would like, we know that the sum of the geometric progression r by 1 minus r to be equal to 1 by 2 minus 1 by 2 power L dash. This will be equal to 2 power L dash minus 1 by 2 power L dash. So in other words, rewriting it again, we will have r by 1 minus r equal to 2 power L dash minus 1 by 2 power L dash. So r times 2 power L dash plus 2 power L dash minus 1 is equal to 2 power L dash minus 1, which gives us r is equal to 2 power L dash minus 1 by 2 power L dash plus 2 power L dash minus 1. Here we can afford to take away minus 1 from both sides. We will be left with the ratio 1 by 3. So the next ratio will be 1 by 3. Similarly, so if we have 1 here, a half here, the next ratio is 1 by 3 here, we will be left with half minus 1 by 3 equal to 1 by 6. So again we try to determine the ratio r such that r by 1 minus r is equal to 1 by 6 minus 1 by 2 power L dash. the viewer can easily see that R will come out to be the value 1 by 7. 1 more than 1 by 6. Similarly, so we will have the ratio here, half, sequence of ratios here, 1 by 3, 1 by 1 by 7, and then we will have 1 by 43. In other words, and so on. So we will have the following sequence, only the denominators here. So T naught is equal to 2, and Ti plus 1 is defined in terms of its previous term Ti as Ti times Ti minus 1 plus 1. So the coding is as follows. So we have M here, 1 by T naught plus or minus 1 by T1 plus or minus 1 by T2 plus or minus 1 by T3 plus or minus and so on plus or minus 1 by TL. There are L plus 1 ratios fixed. We code only the plus or minuses or ones there as ones or zeros in the code. Up to L plus 1 ratios are assumed. And as we can see, the value of Ti plus 1 is defined as Ti times Ti minus 1 plus 1. So more or less squares each time. The sequence of values of Ti for a few terms alone are as follows. Basically, we will have the ratio 2, 3, 7, 43, 1807, and 3, 2, 6, 3, 4, 4, 3, and so on. As we can see, these appear to be prime numbers or a subset of the primes which has this interesting property. So this sequence more or less squares each time. So the large for TL, for even L equal to say 16 or so, that will be squaring up to 16 times, which will be very, very large. So a very large number can be fairly accurately coded this way using this ordered hash function, where the idea is to code where they use the data value to represent an operation here, plus or minus.